Y'all know what the base of the numbering system is. I don't know how y'all learn numbering systems in school, but we'll show you the way it actually is. We're going to be dealing with 4 number systems: decimal, binary, octal. We teach this, and you'll definitely run and you get this in PLCs. So PLCs are computers. There you go, Bill. So we're going to be looking at decimal, binary, octal, and hexadecimal. Of course, these are just a pretest, right? Y'all understand that? So everything we're going to talk about that's up here, we're going to go through in this chapter. Anybody know what a bit, a nibble, a byte, a word is? What's a byte? Yeah, but what is it? Oh. You've heard of it before, but you don't know what it is. You've heard of it. And then what's a binary? Kilo, mega, and giga, tera, by the way. I should add that on. We're hearing about drives that have the ability to do terabytes worth of information now, so we'll look and see what tera is also. But not in base 10, not in decimal, but in binary. So it's a little different, guys, in binary. So we're going to learn that today. So we know a little bit about digital. We talked about this last class just a little bit. We have 2 ways we can send information. We can either send it digitally or we can send it using analog. We talked about a lot of people think that digital is more precise, but that's not true. Analog is more precise. The problem we have with analog is what? What's the problem with the analog? What's the disadvantage of analog? Yeah, we have problems with sending that information over distance, right? Because it degrades over distance. And what's our other problem? We can't store it for later use. I mean, we can't store analog values for later use, right? There's really no real way to do that. And what's the third disadvantage of analog? No, speed. Right. Analog, we could be just as fast as digital. In fact, digital, a lot of times to actually transmit it, it's digital, but we transmit it on an analog signal. We call it a carrier. The biggest thing is actually processing the information that we receive. You can't do math with analog. It's hard to do electronically. You know, I could add 5 volts and 10 volts, but it would be hard for me to design an electrical circuit or electronic circuit that would add those, right? You don't understand that. Logic, it's hard to do logic, and, or, this and this is true, or this is true, or this, not that is true, and that's what we call logic. It's hard to design circuits to do logic with analog. So that's why more and more devices are going to digital. So, by the way, I got this watch on my hand. I didn't turn my thing. But if you see a second hand jumping between seconds, that's digital. An analog watch would sweep. You'll understand the difference. So if you see it jumping between seconds, like my watch I've got on my arm, it jumps between seconds. An analog clock would do what? It would constantly sweep. So here, this is an overview. I'm just showing the watch. Just about all the watches that we have now are more than watches. They're smart watches. They do a lot of stuff for us now, but those are digital devices, right? An analog is constantly varying. It has the ability to constantly vary. It can literally have an infinite number of combinations between the maximum and the minimum. Digital is going to move in steps, right? You understand that? Well, we can electronically control it, really. we don't see many CDs anymore. But what we have to understand is we live in an analog world. The world is analog, right? You understand that? Temperature is what? Analog. Light is analog. Pressure is analog. But we've got this computer right here that is what? Digital. So we have analog to digital converters. We have electronic circuits that can take analog and convert it to a digital equivalent. And then we've also got circuits that takes digital and converts it over to an analog equivalent. But it's not true. I'll have to look up this guy. Let me see if my camera will. So if you looked at it, this is a digital oscilloscope that we're getting. Now, oscilloscope is a device that actually shows you, so meters average everything. So you get into a signal, you take your DC meter and put it on a circuit. Now normally it's okay, but if we were to come up and take a digital meter and put it into a circuit that had a digital signal on it, then what it would do, it would come up here and average it out. So if I was to come up here and so if I was to come over here and look at a digital signal like this, you know, I'm trying to make them the same. And this right here was plus 5 volts, and I put my meter on that. What would you think the meter would measure? It's going to measure 2.5 volts because it's giving you the average, right? You understand that? So that's the problem with a meter. Just because you take a meter, and everybody's used a meter in here at this point, you put it in a circuit, it gives you what? The average. If I come up here and looked at AC does this. Well, we say we have 120 volts AC, but from this point to this point, this is actually around 340 volts. But your meter measures at 120 because it's giving you the what? It's giving you the average. Actually, it's a root mean square, but it is a means of getting an average out of it. So what an oscilloscope does, an oscilloscope actually shows you it draws a picture of what's actually there relative to time. Okay, does that make sense? So if I was to come up here and take this guy, so this guy just plugged in. Let me get my camera up. Well, if you see this little guy over here, if it's not there, it means it's what? It's not recording. But every one of these numbers, we're going to do this for you. Now, look at this. What we're doing is just binary right now, right? Binary. All I was asking is, I was noticed when y'all was writing down the binary number, what was y'all doing? Now, this is not too bad, but, you know, we're dealing with 64-bit processors right now. 64-bit. And you're trying to write down that number. There's no way in the world you're going to write down that number correctly, right? So what we got for the whole number? What's that? Can be 282. What we have is anytime I add an odd number plus an odd number, I'll always get an even number. Anytime I add an even number plus an even number, it will always give me an even number. There's only one way we can get an odd number. Only one way we can get an odd number. And that's if I add an even number plus an odd number. This number right here is the only odd number that we have in the whole binary system right there. So that means if that bit is if that bit is a 1, then my decimal equivalent had better be odd. If that number is a 0, then my decimal number had better be even. Now, it don't mean if you get an even number when you expect an even number, or an odd number when you expect an odd number, it doesn't mean it's right, but it has a chance of being right. So I know that whole number is an odd number. Why?
75.
Huh?
I got 75.
75 might be right. 75 has a chance of being right. Understand? This would be 2, this would be 4, this would be 8, this would be 16, this would be 32, this would be 64, this would be 128. So if I had 64 and 8, 64 and this, and 64 and that, I'll always get, so I'm always adding an even number plus an even number, right?
So the first one, the first digit, or the first bit, that's not a 2?
No, it's a 1. It's 2 to the 0.
Okay. So
I mean, that would be like saying over here on base 10. So that would be like here on base 10, you're saying this is a 10 to the first. And it's not. It's a 10 to the 0, right? You understand that? So your first number, your first weight on the left-hand side of the binary point is 10. It would be 2 to the 0. And any number raised to the 0 would be what? Is a 1.
Okay, so that's why I messed up at. But the first bit that I had on there was 2.
Yeah. But you understand, right?
Yeah.
And you can understand why you got a lot bigger number, because you were up here on 256 instead of what?
Instead of 128.
1, 2, 4, 8, 16, 32, 64, 112. So I know my answer. I know my whole number. It got to be odd, and I know it's got to be greater than 128. Right? You understand that? Yes or no? So that gives me two things. That gives me a chance of being right.
Okay, I got it now. So it won't be 75 because it's not greater than 128. It won't be 75 because it's not greater.
Right. So it's got to be greater than the most significant bit, whatever the most significant bit is. So my most significant out here is what?
128.
So I know my answer's got to be greater than 128.
It'd be 141.
And I know it's got to be an odd number. Why? Because that least significant bit, or that first bit is set right in the whole number. So if it's a 0, then my answer's got to be even. If it's a 1, my answer's got to be what? Odd. Y'all understand what we're saying? Yes or no? We're talking about what guy? That guy right there. Because that's the only, so this right here determines whether it's an even or an odd number. So what we got? What's that? 141.75. Huh?
Yeah, that's like that.
141.75. So what over here? This would be over here. It's numbers. Over here is we go by the same. We've already used 2 to the 0, right? You understand that? So 0 has no weight. So when we go over on the other side of the radix point, we would be 2 to the -1. Now, but we do the same thing. It's just that we're going to start right here, right? Because we've already used that one. Everybody understand that? So this is going to be the reciprocal of that. So that'd be 1/2, and this right here would be what? 1/4, and then we keep going. 1/4, 1/8, 1/16. Everybody okay? I'll do another one. I kept it a while ago, so let me get rid of it. Dang it. Got some cords here. Now, don't worry about the number on the right-hand side. This is base 16. But what I'm trying to get across to you is binary numbers become very cumbersome because your ones and zeros are going to do what? They're going to start running together. But if I was to convey this binary number as 175.5, every one of y'all would have written that down right? That's not the weight of the number. That's the number, that's this binary number represented in a base called hexadecimal. So when we look at this, we think it's a big number just because of the number of digits. But remember, on base 10, each of those guys holds a weight of a power of 10. Here, these guys only hold a weight of a power of 2. So it means it's going to take a lot more bits to represent numbers because of the resolution of the number system. So I gave y'all another odd number, right? What's that? 273.373. It has a chance of being right? We got one answer, 373.625. Huh? That's what you got? Are we okay? Huh? 357? One, 2, 4, 8, 16, 32, 64, 128, 256. So I know it's got to be greater than 1, 256. I know it's got to be odd. So Michael's number sounds right? You understand that? So what am I going to add? I'm going to add 256, 64, 32, 16, and 5. I can do 4 and 1 in my head, right? Okay, Michael? See where you went wrong? We're okay. Everybody okay? Any questions? Now, that's binary to decimal. Now I have a feeling of the weight of the number. But I should have did what? I'm going to subscript this with a little that tells me it's what base. This number right here, this combination of symbols would be legal in base 8, and that would be legal in base 16. They all have different weights depending on what base we're looking at, right? You understand? So this is why we're going to make sure we come back here and subscript this. Just so you understand the base. Make sure you know what number. That top number that we're in binary, that would be legal in every base that we're going to deal with, because notice binary uses ones and zeros, uses those symbols. Decimal uses those symbols. Hex uses those symbols, and octal uses those symbols. So this I'll make sure. Now on the test, it'll say convert this binary number over to decimal, and you'll know from that it'll be what base it is. Anybody want to work another one?
I'm good right now.
All right.
It's too early to keep using my brain like this.
It's good for you. It wakes you up.
Oh, Lord.
Okay, guys, let's take a 2-minute break. So this would be counting in binary. So what I've done is I've put binary and then, of course, the decimal equivalent next to it. So 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. This is the way we would count in binary, right? Everybody okay? Make sense? Yes or no? Huh? What don't make sense? This is the way we would count in binary. So I'd start off counting with 0. Normally, when we start off counting, we start off counting with 1, but actually we'll start off with the actual first digit. So this would be 0, this would be 1, which has a decimal equivalent of 1, right? You understand? Then this would be 1, 0, which has a decimal equivalent of what? 2. Right? Y'all understand that? This would be 1, 1, which has a decimal, so that would be 2 to the first, 2 to the 0 plus 2, right? You understand that? That would be 3. This right here, 1, 0, 0, 1, 0, 1. So you can see how we count. So it's just like counting in decimal. So I come up here and I start counting in decimal. And if I start 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I need to keep counting. What do I do? I've hit the base. I need to keep counting. What do I do? I add another digit, right? You understand? And then I start all over again. So I add another digit right here, right? You understand? And then I'll start all over again, right? And then I'll start here and I'll count until I run out of combinations, right? You understand? Over on this side. I've run out of combinations over here, so what do I need to do? I'll increase this to what? I'll go to 20, and I'll keep counting and counting and counting until I get up to 99. I can't go any further unless I add another what? Digit. Well, in binary, guys, we've only got 2 digits. What are they? 0 and 1. So I come over here and I start counting. 0 and 1. I've run out of combinations with 1 bit, so what do I got to do? I add another bit and I start over. Right? So I add another bit and I start over. Well, heck, I've run out of combinations again. What do I need to do? I can't go to 2, so I add another bit and start over, right? You understand that? So this would be 4, 5, 6, 7, 8, 9. Oh, I run out of combinations. What do I do? Add another bit to the left and start all over. 9, 10, 11, 12, 13, 14, 15, 16. Run out of combinations. What do I need to do? Add another bit and start over. Add another bit and start over, right? You understand that? Okay. 16, 17, 18, 19. I run out of combinations. Add another bit and start over, right? You see that? And that's the same thing you're doing in decimal. But decimal, we add another one every time we get up to 9. Here we got to add another one every time we get up to what? To 1. Because there's no such thing as a 2 in the binary number system. That symbol, we don't use that symbol in the binary number system. Here I went all the way up to 47. Well, we could just keep going. So what would my next combination be? I'd go 1, right, and then do what? 0, 0, 0. Then I'd start over with this guy again, right? You understand? And we just keep going. And the binary number system is very complex. Well, I'm sorry. It's not complex. It's very simple, but it's very easy for us to make mistakes when I get big binary numbers because we get the 1s and 0s all tangled up in our head. So there's got to be a better way that we can convey information. So everybody okay? So the one furthest to the left, we call this the what? We call this the least significant bit. And bit should be lowercase, even though you get paste, people don't do that. And the digit furthest to the right, we call this the least significant bit. Everybody okay there? Huh?
Yeah, the one to the far left is the most.
Oh, I'm sorry. I think I said most, but okay. The one to the far left, but it should be most. We both early, 8 o'clock's early for both of them. Now, how are we going to go from decimal to binary? Well, when you get to the textbook, it's going to use something called successive division. And what's nice about successive division is this works from any base to whatever base we want to convert it over to. Now the way successive division works is we'll take a number, okay, this makes sense, and then I'll start dividing it by the base. And what would I come up and get? Let me go over here to this one. So 1, 2, 3. Let's don't do one that big. Let's do one a little smaller, because this is the one I recommend that you don't use. And we'll start off, by the way, you can buy a calculator that converts between bases for you. But I'm a firm believer, if you don't know how to do the math, you don't need to use a calculator, right? Because you have no idea if the calculator is giving you the right number. Plus, you understand the format. So even this Windows calculator right here, let me get back here. The Windows calculator is a really neat calculator. So I can come up here, right here, and view, and then I can go to the programmer's calculator, and then I can come up here and put it in binary, and I can come up here and just type in a bunch of ones and zeros. And then it's going to, I come over here, okay, I want to look at that, that's hexadecimal. That would be decimal, that would be octal, and that would be binary. Now that's good, but you don't understand how we come up with those. You're just using a calculator to get an answer, right? Understand? So the first test that we have, you're not going to be able to use a calculator on that test. You're going to be able to use this powers chart right here, right? You understand? And then everything else is going to be long. And we're going to do a worksheet. I'm going to give you a worksheet today. And if you can do this worksheet, then you're not going to have any problems with the test. But you need to do it longhand, right? You don't need to do it with a calculator, because if you use a calculator, you're going to fail it on the test, right? So we'll come in here, we'll go over the worksheet. You've got every answer right, which I say, okay, this guy's got it down. We'll give you the test, and you failed the test because you did a what? You did it with a calculator. Worksheets. And people's had my class before. The way I grade worksheets is if you try, if you attempt, right? Understand that. Not if the answers on the worksheet are correct or not, because you're learning how to do this. So let's do a number. Let's do a smaller number. Let's do 257. So I know I should end up with an odd binary number, right? Understand? Now, the way the book teaches, they use it what they call successive division, which means we come up here. And what's nice about 2 is most people can divide by 2 on a longhand, right? You understand that. But if you want to use your calculator right now, that's fine. I'm going to divide this by 2. Now, what does that give me? What's that? What's that? 128.5. Now, the way we can get the whole number represented by a fraction is we can come up here and take that whole number and multiply it by whatever we divide by. So I know 0.5. So if I was going to do this longhand, I would come over here and I would put that little thing right there, right? You understand that? Remember how y'all did this when y'all first learned to do this? And I'd say 2, 2, 5, 7. I would come over, I get 128, and then we'd put a little R, and then we put a remainder of 1. That's before we learned fractions, right? Remember that? So we're looking for the whole number remainder, not the fraction. Well, I know the whole number, if it's got a 0.5, the whole number remainder is going to be 1. Right? You understand? So what I'm going to do is I'm going to write the whole number remainder over here, and then I'm going to bring down this number right here, 128. So I'm bringing down this right here, right? And then I'm going to divide that by 2. Well, what's 128 divided by 2? 64 with a remainder of what? 0. Then I'm going to take, since I didn't, then I'm going to bring down the whole number, 64 divided by 2. What does that give me? With a remainder of what? 0. Okay. Then I'm going to take the 32 and I'm going to divide by, this is an easy number, guys. I'm going to divide by 2. What does that give me? 16 with a remainder of what? 0. And then I'm going to come over here and I'm going to take 16. I'm going to divide it by 2. This gives me 8 with a remainder of 0. Then I'm going to take 8 and divide it by 2. This is going to give me what? 4 with a remainder of 0. Then I'm going to take the 4 and divide it by 2. This is going to give me what? 2 with a remainder of 0. I'm going to take 2 divided by 2 is going to give me 0.5, which would give me a remainder of 1. 0 with a remainder of 1. Now what we do is we let the number fall this way. So this is why I should have used another, 2 divided by 2. It's always divided by 2, which would give me 1, right? Which would give me a remainder of 1, right? It'll go 0 times with a remainder of 1, right? Y'all understand that? So what's going to happen is this last guy is always going to be a 1, because sooner or later we're going to. Everybody okay?
So you said that the top number would be to the far right. You work your way to the left as you go down.
Yeah, let's do it. Let's do another number that don't work out like this. So what's 136 divided by 2? So I should have went one more, by the way. So y'all were right. So this would be what? 68, right? And what's my remainder going to be? 0, right? And 68 divided by 2. So that other one should have been 0, right? With a remainder of 1. I'm sorry. So this would be 2. What would this be? 34 with a remainder of 1, right?
And 68.
We okay?
That's 68.
Oh, I'm sorry. Thank you. Where did I get 65 from? So 68 is going to be 34 with a remainder of 0. And 34 divided by 2 is going to be what? 17. What's that? 17 with a remainder of what? 0. And 17 divided by 2 is going to be what? 8 with a remainder of 1, whole number remainder of 1, right?
Okay, yeah.
So anytime you have a 0.5,
It's gonna be 1.
then we need to get it to the whole number remainder, right? And this is going to be 8 divided by 2, which is going to be what? 4 with a remainder of what? 0. Then we're going to take 4 divided by 2. This is going to be what? 2 with a remainder of what? 0. Then I'm going to say 2 divided by 2. This is going to be what? It's going to be 1 with a remainder of what? 0. That's where I stopped a while ago. Then we're going to have 1 divided by 2. So this is right. This is going to be a 0.5 with a remainder of what? 1. Everybody see where I stopped a while ago? I stopped at the wrong spot. Okay, now what we're going to do to get the binary number is we're going to let this thing fall this way. So I'm going to say 1, 0, 0, 0, 1, 0, 0, 0. Now if this works, I should be able to convert that to decimal. 1, 2, 4, and this is one way you check your work. You take your binary number and you convert it back to decimal, and you better come up and get the same number that you started with, right? 8, 16, 32, 64, 128. So I'm going to take 128, and I'm going to add 8 to it, and that gives me 136, so that it worked out.
So that's how you got the plus 8 by adding how many bits you have up there?
No, I come over here and I'm converting from binary to decimal. So what I do to convert from binary to decimal is I start off by writing powers of twos. We just got through with this, right? I would say that would be 1, 4, right? 1, 2, 4, 8, 16, 32, 64, 128. I add the decimal equivalents to the bits that have 1 in them. So I have a 1 right here, and that's in the what position? That's on the 128. And then I have a 1 in the 8 position, and that gives me 136. Okay. So a while ago, when I said 2 divided by 2, I should have said 1, right? You understand? Everybody understand that? Okay. Everybody okay? So doing this method, let's see if y'all can convert a number 257 over. And we're not dealing with fractions, by the way. And we want to take this over to binary. Using successive division. And you're going to find out, odds are, this is not the one you're going to use, but this is the way the book teaches. This is the way. Huh? No, that was wrong, but I gave y'all the wrong answer. So the one we came up with was wrong because I said 2 divided by 2. Well, 2 divided by 2 is 1, right? You understand? With a remainder of 0. So we should have went one more bit. So the way I did it wasn't right. We got 1. Then another 1. Yes, a while ago we stopped right here and we should have went one more bit. Huh?
Okay, the last step, 4 divided by 2, or divide 2 by 2.
Equals 1 with a remainder of 0. And then you got to bring the 1 down. So that's where we stopped a while ago. Yeah, you have to bring the 1 down.
So for right now, as far as we know, we're not going to be dealing with decimal, correct?
Yes, we are. The problem is we got to deal with decimal because that's the only thing I understand.
No, I'm talking about as in a half or a fourth or an eighth or something like that.
Oh, you mean the decimal point?
Decimal point.
The radius point. Yeah. That's what got me.
So right now,
Fractions. We're not dealing with fractions.
Okay.
Well, we do the same way, but it's a little harder. So when we do this method, we're not going to. The other method that I'm going to show y'all, it's fractions works out. This guy right here it's hard for fractions because you got to multiply by 2 and it gets very, very confusing. So this method, all we're going to do is teach whole numbers. It's a good point, I think. Y'all want to do another one? Or anybody want to go through this? Because this was, y'all notice I said I could have done that in my head because I know that. Because I know 256 is a power of 2. So anybody want to see this work? Huh? Let's do one that's got more 1s in it. So even or odd number? That's a big surprise. So let's say let's keep them. We'll keep them. Still keep them kind of small, right? Let's do 209. You could do these any size decimal number. You could do that, and this works, by the way, for any base. So you take the base 10 number and you divide it by whatever base you want to convert it into, right? This works for any base. What's nice about this though is 0.5 is going to give you a 1. But 0.5 in base 16 is going to give you 8, right? You understand that? And 0.5 in base 7. So it gets a little harder to come up with the whole number remainder in the other bases.
I don't know if this writing has to.
It doesn't hurt. Here it don't hurt being wrong.
I got 8 1 and a 0.
Could be right. Could be right, because we know it's got to be greater than what? 256. And we know it's got to be even. Could be right. Anybody else got anything different?
What at the bottom? Log of the book is 1 divided by 2.
Because when anything we do, any number we do, the most significant bit's got to be a 1. We're not going to end with a 0 up there, right? Understand that? So your last one is going to be, your last thing should always end up with 1 divided by 2, right? On this technique right there. That's a good point. So, and we know about how big the number is, you're going to go down and eventually you're going to come up with, the very last one is going to be 1 divided by 2. Because this guy right here is when you do this guy up here is always going to be a 1, right?
Yeah.
Yeah, it's always got to be. The most significant bit on this situation here will always be a 1. The least significant bit is going to be either a 1 or a 0, depending on whether it's an even number or odd number. Anybody else got a different answer? You do? What do you have?
I have.
Wait a minute. Let me erase. That's what you got?
I got 0 1
Well, this is not going to be a 0. We're going to start, when you read numbers, you always read from the most significant digit, right? Okay, so start with the most significant digit. Huh? Yeah, your most significant digit is going to be a 1. It's always going to end up with 1 divided by 2. No matter what you do, it's always going to end up 1 divided by 2.
Yeah, then it's going to be 0.
You got 1,
Yeah.
0.
Yes. No, yeah, 0. And then 1. 0.
0, 0, 1, 0.
Yeah.
That's what you got? Well, what we need to do is just go back and check it. So I'm going to go 1, 2, 4, 8, 16, 32, 64, 128, 256. I'm going to add what? 256. I'm going to add 32. And I'm going to add 2. Right? Okay. So this is going to be what? 10. Carry 1. This is going to be 9. 2. So y'all understand. Just go back and do what? You went from decimal to binary, and then you can go from binary back to decimal. I was in college and taking a class at Jeff State in algebra. I flew through that test and go back and check my answers. I thought I made 100. That made like a 75. And all my mistakes were what? Yeah, they were. So what I did after that, I went back and checked every answer and I aced every test after that. So it's always good to know how to go back and on these math and do one. Even in division. So you divide, then you should be able to multiply it back out and end up with the same number you divided into, right? Okay, let's look at this technique. Everybody here we're having to do a little math, right? You understand that?
Now for this one, what I didn't understand, I knew I was wrong because I had too many ones, first of all. But when I divided 145, well, 127 divided by 2, I got 63.5.
Let's see. Well, let's do it. So let's divide by 2. So what's 190 divided by 2? Okay, what's that? 145, right? With a 0 remaining. Okay. Then I'm going to take 145 and divide it by 2. That's going to be 72.5. Yeah.
Oh, that's why I messed up originally. So I didn't worry about it. I was talking about
72 divided by 2.
And 72 divided by 2. You're okay?
yeah, I'm good now. Yeah.
Everybody else okay? Let's look at it this way. So we got this, we got 290. So this is the way I prefer. So what I do is I just start writing down a power of 2 chart. This to me is easier to do, especially on these other bases. I'm going to say 1, 2, 4, 8, 16, 32, 64, 128, 256, and I always go one number past because I want to make sure I got enough bits up here. Then what I'm going to do is I'm going to come over here. I've got 290. This is the number I want to convert. I'm going to figure out what is the highest decimal equivalent of a power of 2 I can subtract from 290. So we're going to subtract this from this, and people get that backwards. I don't know why. So the biggest number I'm going to subtract, the biggest thing I can subtract is a 256. So what I'm going to do, I know I got at least a 256 in that number, right? You understand? And what do I end up with? What's that? Everybody okay? Okay. Can I subtract a 128 from that? So I'm going to put a what over there? A 0. Can I subtract a 64 from that? No. So I'm going to put a what? A 0. Can I subtract a 32? I'm going to write down a 32, right? You understand that? Put a 1 over there. What does that give me? That gives me 2. So I'm going to come up here. I'm just going to fill in everything now because I'm to that point. Because that's not the way the book teaches it. To me, this is a subtraction. Subtraction. Subtract. Even going from decimal to these other bases, we're not going to use that divide because it gets so complicated. We're going to go through binary. So we can go from base 8 to binary just like that, guys. When we show you that, we can go from binary to base 8 just like that. We can go other way just like that by going through binary using this technique right here. But the problem, where's the big mistake people make? Well, the big mistake people make is they want to subtract that from this. And they end up all screwed up. This is where you're going to. That's what you're going from. So you're taking what you're going from and subtracting what you're going to. Right? You understand that? So the biggest mistake, somebody's going to make that in this class. I have never taught a class where somebody didn't get that confused. So let's use this method. Of course, you can use either method you want to on the test. So let's bump up our number. So now we're bumping up our number, right? So this is pretty easy, especially after you learn your powers of 2s. But Y'all don't even need to learn your powers of twos because you're going to have the chart, right? But it just doubles every time, right? So let's do 1,763, and let's convert that to binary using the subtraction method. So I'm going to do what? I'm going to start off with my chart. Don't start with 0. Start with what? 1, right? What would it be? 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024, 2,048. You can stop at 1,024. I like to always go 1 over to make sure I've got. By the way, when you subtract, if you get down to this guy right here and you still need to subtract some more, then you screwed up somewhere. So either by the time we get to an odd number, we'll get to this guy, right? Understand? If it's an even number, we're going to run out of subtraction up in here somewhere. And then what do? You just fill in the rest with what? With 0. So I know this is going to be an odd number, so I know I better subtract all the way down to here. But by the time I get there, guys, it better be 1, right? So if you get down to that 2 to the 0 bit, and you still got to do some more subtraction on a whole number, then you know you did what? You screwed up somewhere. So I'll never use this bit right here. I just made sure I had enough, right? Okay, we start off with a what? I know we're going to have a what? 1 comes next. Oh, somebody else still working. We got 3 1s. Okay, thank you. I think say I could add that up in my head and see that we're going to. That's going to be over. One. So these numbers are equal to each other, right? You understand? They are exactly equal. We're looking at the same number in 2 different bases. Look how much bigger the binary number looks than the decimal number. Because the binary number only has 2 combinations where the decimal number has 10, right? So that means we can represent bigger numbers with fewer digits with base 10 than we can with binary. But this is what the computer uses, guys. Everything you see up on this screen is nothing but 1 and 0. So I store a pattern of 1s and 0s into the memory that sets up the display, and then the computer decides what to turn on and what to turn off. So what you're looking at is just things being turned on and things being turned off, right? You understand? And we use 4 prime colors. We use red, green, blue, and then black. So notice the background of my display. You can see it up here. The background of my display is black, right? So what my projector is doing is blocking all those. Then it combines those 4 colors to create all the different colors that we see. Except I think Sony came out with one that added yellow. Nobody could tell, but they use that as a selling feature. Are we okay? Pretty neat. And we can go now we can go to the fractional portion. So let's do a real small number and come up and do a fraction. So what am I going to do? On my fraction side, it's going to be what? 0.5, 0.25, 0.125, right? Now the problem we have with fractions, and this is where computers get run into problems is over on that fractional component over there. Because on a base 10, my first digit is 1/10. On binary, my first digit weight is 1/2. So there's a lot of fractions that would either go out to infinity on binary really, really fast, or it would go out to an extremely large number of digits to be able to handle that. So sooner or later on the fractional portion, your computer's going to give up, right? Just like your calculator. Your calculator can only do so many digits. And then once you exceed the number of digits your calculator can do, what it does is usually jump into scientific notation. And as soon as it jumps into scientific notation, then you've lost digits right over on the fractional component. Y'all understand that? And now your computer becomes less accurate. So how accurate a computer can do a binary, do a fraction depends on how many digits the operating system allows on that right-hand side. In our calculators now, good gracious, most calculators that you buy are limited to, they display 10 digits, but they calculate 13 for rounding. So let's look at the fractional portion and see if y'all can figure out how to do this. So let's do let's just do a fraction, 0.325. So what I'm gonna do is I'll start off now. So here's my binary point, and what's the first thing I'm gonna write down? I'm gonna write down a 0.5, right? Next time I'm gonna write down a what? A 0.25, and the next thing I'm gonna write down is a 0.125, and y'all might help me after this, 0.0625 or something like that. So this will be 1/2. This would be 1/4. This would be 1/8, and the next one would be 1/16. So what's 1/16, guys? I should know that. 2.5. So I was right. I just want to make sure. So I'm going to say, okay. So what's the biggest thing I could subtract from that? I can't subtract this. I'm going to put a what? 0. Everybody okay? Then I'm going to say 0.325. I can subtract this. So I'm going to subtract a what? A 0.25. And I'm going to put a 1 down there. And what does that leave? What? I'm waiting. Got a bar over here, right? So that's going to be a 2. Makes this a 12. 1, 7, 5. Okay? All right? Yes, no? Then I would do what? Can I subtract this? I'd say yes. I'd put that down there. And then I'd subtract a 125, which is going to give me a what? 0.50. I can't subtract that, so I would go off to a different number, right? And eventually, guys, with binary, we're going to have a real problem representing fractions because of the resolution of the binary number system. In digital, we use 0.6 every once in a while. 0.6 would go out. In the decimal number system, I could represent it with 0.6. In the binary number system, it would go way out there. I do something wrong? Oh, this guy? It's not 0.1? Okay, yeah, thank you. I can't subtract. Point what? 0.75. So this is going to be a 0 right here. But we can subtract a 0.0625, right? So it'd be a 1. And what would that give us? So it'd be 5. We had to borrow from this, right? So that's going to be a what? A 2. And then it's going to be a 0. So that means if I wanted to go accurate, the best thing I do would be a what? A 32nd. What's a 32nd? It's going to be half of this. And you could just do what? You could just keep going on. So it's just like on on decimal numbers, eventually on that fractional portion, you're just going to have to do what? Well, eventually you're going to have to give up. So like 1/3. How far would 1/3 go? 333, right? So you say you're going to be at, but still, base 10 on the fractional portion is a lot more accurate than base 2, because base 2, the best, I start off with a what? I start off with a 0.5. On decimal, we start off with a 10. But the subtraction method still works, right? You understand that, whether you're dealing with a fraction or whether you're dealing with a whole number. Now, this class, we're going to primarily deal with whole numbers. So whether you use repetitive division or whether you use successive subtraction, that's up to you. I like subtraction. Are we okay? Damon's going.
Okay, the 75. And the 65. How do you do this?
We borrowed from this, made this a 12, made this a 2, made this a 12. 2 minus 5 is 7. 5 minus 0, if you wanted to put the 0 in there, would be 0.75.
So what about the other 5?
Well, then we couldn't do a 0.075, we couldn't do a 0.125, right, you understand? So we dropped down to a what? 0.0, yeah, I'm sorry. Yeah, 0.065. It's 1/2 of this. So what you would do, guys, you'd start here and you would half it every time, right? Yeah, 5, yeah, it's 3. No, sorry.
You had to borrow that 0 up there. That'll make it.
It's right, yeah. So I just don't bring down my 5. I subtract it from what? Yeah, sorry, yeah. So that's a 0 up there. We're subtracting. So what happened is that's a 0 up there, right? And I'm subtracting this from that. So what did I have to do? I had to borrow from this, made it a 4, right? Made this a 10. And then that would be 5. Then 4 minus 2 is 2. And then, understand, Brian? Yeah, you said bring down the 5, but technically we're subtracting it from 0. I just didn't put the 0 up there. Are we okay?
We don't need to do no fraction. That's all.
On the worksheet, so we're not going to do any fraction, but you know it's available to you, right? You understand? Okay, some terms. We need to know these terms, guys. So a single binary digit we call a what? Yeah. And I always thought that whoever came up with these terms must have been hungry when they was doing this. Because, so a group of 4, we called it a what? Nibble. A group of 8, now y'all know what a byte is. A byte is a group of 8, groups of 8s. And that really bothers me when people start talking about how much memory they use the term gigs or megs, but it's truly megabytes. So the memory in a computer, whether it's a 64-bit computer or what, is set off in groups of 8s. It's just that if I want to access 16 bits, I do it in two bytes, right? So a byte is a group of 8 consecutive binary bits, and then they jumped out of that, and then they went to a term called a word. A word is a group of what? 16. Then Microsoft started calling a 32-bit word, they just called it a double word. But for some reason in PLCs, in programmable logic controllers, they picked up the term long. So those two words are interchangeable. In the PLC community, they're going to call it a long word. In computers, they're going to call it a double bit.
So basically, everything you really double, like 4 to 8, 16, 18, is just double.
Well, we go from a bit to a nibble, right? So that doesn't double.
No.
So that we jump from a bit. So there's no name for a group of 2. There's no name for a group of, so it's 4. So we go from 1 to 4, and then after that, everything. And then we have what we call, in computers, they call it a quad word. So if I was inside the registry of this computer that keeps up how to configure the machine, they would call it a quad word. If I was in PLCs, they would call it a double long word, which is a group of 64 bits. And that's where we're at right now. And I don't know if it'll ever go by that. 64 bits are big numbers. We okay? Everybody okay? Any questions? Huh? Which I know y'all got this PowerPoint I need to upgrade. I was working on it last night and I had posted the newest version on Blackboard. I'll be tomorrow before I can do that because I'm in class all day long. Are we okay? So, what you got to understand is that this computer has no idea what octal is. This computer has no idea what hexadecimal is. All it understands is ones and zeros. But ones and zeros get so dang complicated, they needed to come up with a method where we could represent real long binary numbers in a base that would be easy for me to convey to you. Now, what you got to understand is that a computer can display anything. It can take one thing and display it as another, right? You understand? All you're seeing up there is a bunch of what? Dots. Yeah, they're dots. That's all they are. In fact, they're not little dots. They're little tiny squares. So on a digital screen, if you ever went back and looked at the old CRTs and you got a big magnifying glass, it would actually be dots. They had little circles up there. But what we do in computers is we have these little old squares. And then we use a group of squares, which we call we use the group of squares into something we call a pixel, which is a picture element, right? And we combine those until we get down as small as we possibly can. So what limits the resolution of the screen? Resolution is a term we use for how precise things can be. So we have the ability to set our resolution, but we never can set it smaller than one group of dots, right? You understand that? And we refer to that as a triad, So you can tell how small your triads are by what's the highest resolution you can do. And by the way, sooner or later you get up to a resolution where you can't see that. So now we're hitting resolutions that are better than we can see, especially when what's nice about our nice screens is used to, if you ever had one of them big projector screens, I don't know if we had one of those, and you got the best resolution by getting further back, right? You understand? Because the further back you get, the dots get smaller. Our screens now, we can put our nose up on the face of them, and the picture is still really, really sharp. But the further you get back, if you set back 10 feet from your screen, then 1024 by 768 don't mean anything. Does that make sense? Because your dots are getting what? Past your resolution. So this is octal. Octal, we use the same combinations that we do in the decimal number system up to 7. So you will never see an 8 in an octal number system. So if you see an 8 in there, either somebody screwed up real bad or it's not an octal number, right? You understand? Could be hex, could be hexadecimal, or it could be decimal. So we might have 1, 3, 5, 7. I know it's an odd number. But this could be legal in 3 different bases right now. It could be legal in base 10, it could be legal in base 8, and it could be legal in base 16. So what I'm going to try to do is always do what? Do that. Now, the way this would work, guys, is if I wanted to figure out what the decimal equivalent was, then this would be 8 to the 0, this would be 8 to the first, this would be 8 squared, and this would be 8 cubed. If I wanted to get this number to decimal, then what I'm going to do is I'm going to come up here and do positional notation. I'm going to say 1 times, instead of putting 8 to the third, I'm going to put the decimal equivalent of 8 to the third. So I'll look at my chart. I find my powers of 8. 8 to the third is equal to 512. This makes sense so far. Then I would say plus 3. Instead of putting 8 to the second, I'm going to put the decimal equivalent of 8 squared. What's 8 squared? 64. I would multiply that times 64. Then I would come over here and I'd say 5 times 8. We're okay there, right? Plus 7. Now I'm not going to put 7 times 1 because I know this last digit on the right, the least significant digit, is always going to be times 1. I would do this math. So what's 1 times 512? Okay. What's 3 times 64? What's that? 192? We okay? 192, right? Okay. What's 5 times 8? Y'all should know that from your multiplication tables. That's what? 40, and then plus 7. I add those together, and that would give me the decimal equivalent. Same way. Same thing we did for binary, same thing we did for decimal. But instead of using my powers, I'm actually using the what? Decimal equivalent of that power. Add these together, should expect an odd number. So what we got? I'm gonna let y'all add it. I'm having a math one.
It's too early. I told you, I'm using my brain way too early.
No, well now it's not. You can't use that excuse now. 751. And this, of course, this is going to be base 10. So this is equal to 751. Now, why does the decimal number look smaller? Because it's got more combinations, right? The decimal number's got 10 combinations per digit. The octal number's only got 8. So normally your decimal number is going to appear to be smaller, but they're not. They are what? They are equal. We're just looking at it in 2 different bases. Now that's not complicated, right? You understand that. Here we might have to use a little calculation, but it's still not beyond being able to do it long. The problem we have is I want to take this number and I want to convert it to binary. Well, we could do this. We could take this and convert it to decimal, and then we can take our decimal number and go to binary, right? I don't understand that. But we don't have to do that, guys. So I could divide by 8. I could use excessive approximation, but now my fractions are going to be a portion of 8. So on my fraction, I would have to take my fraction, instead of multiply it by 2, I'd have to multiply it by 8, right? You understand that? So we could do it that way. But I don't want to do it that way. What they did is they're saying, okay, so what I'm going to do, I made that number up. I have not done this pre to this class, right? What I'm going to do over here is I'm going to come over here and I'm going to start writing down a binary number. Base 2. Let's convert this over. So this is going to be 1, 2, 4. What you mean? No, we can drop those. We're not doing the subtraction. I just did this in my head, right? You understand? Of course, when I do this, when I convert it over to decimal, I'm just gonna ignore those zeros, those most significant zeros, and we'll see why in a minute. 4, 8, 16, 32, 64, 128, 256, 53. Okay, so I'm going to come up here, I'm going to add 512 plus 128 plus 64 plus 32 plus 15, which is 8 plus 4 plus 2. Add those up and see what you come up with. And why did I know that? Because I know that add. What do we got? Anybody got it added yet? Do I need to make it bigger? What's that? 751. My goodness. So I went from that octal number to binary. I did absolutely no math. I did it. And I could come up with any octal number you want. And I could convert it to binary. Without even one. Without even thinking about it. So, which would be easier for me to give you if you didn't see up here on the board? I said, okay, everybody write this down. 1 0 1 1 1 0 1 1 1 1. How many would have got that written down? Nobody. But if I had said 1 3 5 7, everybody would have got that right. So when I'm trying to convey this binary number to you, if I could do that in base 8, it would be a lot more accurate because I'm conveying digits to you, right? You understand? That's easier to understand. But I can do this with any number. So I could come over here and I can say, okay, let's take a binary number and convert it to octal. So I'm just going to make up a binary number. Now what I'm going to do is I'm going to come up here and I'm going to split this into groups of 3s. Don't let me mess up. I see it now. Everybody see that? Then I'm going to come up here and I'm going to say, okay, what would the weight of this number if it was by itself? This would be a 1, this would be a 3, this would be a 2, this would be a 7, this would be a 2, and that would be a 5. I just converted that number to base 8. I guarantee you, if you took these two numbers and convert them over to decimal, you would have exactly the same. So instead of us doing this, let's do it with our calculator. So I'm going to put it in binary. I'm going to say 1 0 1 1 0 1 0 1 1 1 0 1 0 1 0 1. Did I mess up? Okay, then I'm going to come over and look at octal. 1 3 2 7 2 5. Oh my goodness, ain't that amazing? Okay. I'm going to take this binary number and I'm going to look in decimal. So that's the decimal equivalent. I'm going to octal, and this would be the same number in hexadecimal. Now notice hexadecimal takes a lot less digits to display this big number. So this is decimal. So it took 1, 2, 3, 4, 5 digits to display that number. Binary is going to be huge, right? Because we've only got, what, 2 combinations. Octal is better than binary, but still the number looks bigger than the decimal number but the hex number, I can display that whole big number. This number right here, I can represent 46,549 with only 4 digits. So how did I do this? Well, the trick is combinations. How many combinations can we get to? Right? Everybody understand that? So octal, we have 8 combinations. So octal, I have 8 combinations. But when I come up here and start writing groups of 3s, so that'd be 0, 1, 2, right? This would be 3, this would be 4, this would be 5, this would be 6, this would be 7. So what I notice is in binary, in octal, every digit has to have 8 combinations, 0 through 7. With 3 bits of binary, it gives me exactly 8 combinations. So 3 bits of binary has 8 combinations. Each digit of octal has 8 combinations. So what I'm doing is I'm substituting each binary combination to represent a digit in octal. So this would be 0 in octal. This would be 1, 2, 3, 4, 5, 6, 7. So what I'm doing is I come over here and I have a binary number. Make it big. Now, it would be almost impossible for y'all to get that number right. So what I'm going to do is I'm going to come over here and I'm going to split this up, starting at the least significant bit. Got to start at the least significant bit. I'm going to split this up into groups of 3s. Now what I'm going to do, I don't have this, you know that this, I can put a 0 right there. I can't put a 0 on this side because that would change the weight of the number. Okay. Then I'm going to look at that pattern. So what pattern represents that guy right there? Okay, so I'm going to write down an octal 2. What pattern is this? 6. A lot of them you can do in your head because now we're only dealing 1, 2, 4, right? You understand? So 4 plus 2 is a 6. This would be a what? A 5. That would be a 3. That would be a 5. That would be a 3. That would be a 6. And that would be a 6. And that's that number in base 8.
Oh, it's easy.
It is easy.
No, not really. Not really.
Oh, Lord.
So now I could call this out like, okay, everybody write this down. 2, 6, 5, 3, 5, 3, 6, 6. Just about everybody would have got that right? Now this was the first numbers that we were dealing with when the processors first came. The first microprocessor came out, by the way, was only dealt with 4 binary bits. It was used in a calculator. You won't see, it was the 4004, it was put out by Intel, and then it was a 4-bit processor. The next one, which got really high probability, was the 8008, and it was an 8-bit processor. And that's why we started, after that, everything started running in groups of 8s instead of. So the 8008, the 8080, the Z80, all these were 8-bit processors. Then the next processor they came out was a 16-bit processor. So why they started out using octal was that these were 8-bit machines. And octal came in groups of 8s. When PLCs, when programmable logic computers came out, it allowed us to enter large binary numbers into the computer using octal instead of using binary. But after that, we started going in groups of 8s, guys. So that's when the hexadecimal came in. So this computer right here predominantly uses hexadecimal to display large binary numbers. So let's say I had an octal number. Let's say I had an octal number and I wanted to go to binary. 3, 7, 6, 2. Well, what I would do is I would start down at the most significant bit, and you got to use 3 bits, right? You understand? Everybody okay? And here's my combinations: 0, 1, 2, 3, 4, 5, 6, and 7. Exactly 8 combinations, right? Well, what I would do is I would start with my most significant digit, and I would write down the pattern. I'm going to include the 0, because you can't drop zeros until you get through with the number. So I'd come down here and I'd write down that pattern, right? You understand that? Then I'd write down that pattern, and then I would write down that pattern, and then I would write down that pattern, and I just converted that number to binary, from multiple to binary. Ain't that slick? So if I wanted to give this big binary number out to you, I start saying, okay, everybody write this down. 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, 0. How many would have got that right? Nobody. But if I'd have said 3, 7, 6, 2, everybody would have wrote that, unless you were snoozing, right? So if I wanted to give you a large binary number, it just makes sense that I give it to you in octal instead of trying to give it to you in binary. So when my computer displays large binary information, all it is a bunch of dots. And one thing a computer can do is it can make things appear like they're really not. So I might have this binary number, and we bring this into the processor, and it turns on the patterns to display 3, 7, 6, 2 for that binary number. Of course, this computer does not display large numbers in binary. It does, in octal. It does it in hexadecimal form. So if I was going to take a number and I was going to convert it to decimal, you can use the power 8 if you want to, right? This would be 8 to 0, 8 to the first, 8 to the second, 8 to the third. If you take the decimal equivalent of 8 to the third, multiply it by 3, and that would give you the decimal number. Or you can go through what? Or you can go through binary, and then you can want, in this class, it's probably that way, because you're going to have to, the way the worksheet is laid out is that it gives you a number somewhere within one of these bases. And then you have to convert it to the other 3. So here's our patterns. And basically all we're dealing with is 1, 2, 4 right now. We're not dealing 1, 2, 4, 8, 16, 32, 1, 2, 4. Right? So if I converted this to decimal, what would that equal to? 0. That would equal to a what? A 1. This would equal to a what? A 2. That would equal to a 3. That would equal to 4. That would equal to 5. That would equal to 6. And that would equal to 7. That's the same digits we have in the what? In the octal number system. So now that I've got my patterns over there, which you can come up real easy, right? This chart is not hard to come up with. Now I could come over here and say, okay, I want to take a binary number. Don't make any difference how long it is. I'm going to do what? I'm going to start with the least significant bit. I'm going to group it into what? Groups of 3s. Now this one worked out. If this don't come up and give me a group of 3, I just pretend there's zeros on the left-hand side, because that's not going to change the weight of the number. Then I just write down the octal equivalent of this. So this would be a what? A 5, 5, 3, 2, and that's base 8. I guarantee you if you took those two numbers and converted them to decimal, they would be exactly the same. Dang, I shut down my calculator. So I'm going to put it in octal, and I'm going to go 5, 5, 3, 2, And then I'm going to convert that to binary, and by George, what do you see? Same thing. Then I could take my binary number. Let's take my binary number and convert it to decimal. So this is going to be what? 1, 2, 4, 8, 16, 32, 64, 128, 256, 5, 5, 12, 1024, 2048. So I'm going to add what? 2048 plus 512 plus 256, 64, 16, 8, 2. Or if you wanted to, you could say what? This is 8 to the 0. This is 8 to the what? First. 8 to the second. 8 to the third. So I could say 5 times 8 to the third. I'll come over and look at my chart. What's 8 to the third? 512. Plus 5 times 64. Plus, I'm running out of room. Plus 3 times 8 plus 2. So whichever one you want to go to decimal. In fact, if you've got this multiplication table, it might be easier to do what? Go from base 8 to decimal. Instead of going from binary to decimal, because you're not dealing with all those powers of 2's. A lot less math, right? You understand? Here I'm only dealing with 1, 2, 3, 4 digits. Here I'm dealing with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 digits. So you could go from decimal to octal by using that divide by 8, right? You understand that? Then take your fraction, multiply it by 8 to give you the whole number, carry the whole number out, and then drop down. That's up to you. To me, it's almost easier just to go through what? Binary. Go through binary just by doing what? Using groups of 3's. So what do we use octal for in computers? Well, this computer right here is binary. That's all it understands, but eventually it's got to convey this binary information to you, even if it's configuring stuff, right? So we can look at all of, so everything in a computer is assigned an address. And those addresses, each address holds 1 byte of information. So when I start looking at the physical access of my computer, and this is still available, so down here under accessories, which most of y'all don't even know about, accessories, then I can go up to the system tools. And then I can look at system information. So this tells me everything about this computer. And then I start looking at hardware, and I start looking at the input-output devices. It's going to give me addresses, but can you see 2C, 4? If I come in and look at memory, look at this weird stuff right here, F253A3FF. Well, that's displaying an address for me. Now that address is a binary number, but instead of displaying it to me in binary number, it's using another base. It's using base 16. So computers use base 16. PLCs use octal, or they use decimal. But when we start doing logic in a PLC, it's almost impossible to do logic with decimal numbers. Because logic is performed with 1s and 0s. So there's no such thing as a number 9, right? Don't understand that. Now we can have a 1001, which is the binary number represented by number 9. It can do logic on that, but it can't do logic on a decimal 9. So when you get into programmable controllers and you start telling your programmable controller to do logic, then you're going to have to enter it. You can enter it in binary, right? Or you can enter it using octal, or you can enter it using hexadecimal. So guys, that's octal. What comes next? X. This is what these guys use. This is what your cell phone uses. Of course, your cell phone is going to display stuff in base 10 for you, right? But it's nothing but dots. So it can see this dot 1001 and turn on dots to display a 9, right? You understand? So your phone has no idea. I don't know on your phone if it does that or not. But when you start dealing with these computers, to really understand the way the computer works, you got to understand the computer is binary. It is digital. It is ones and zeros. Everything's got to be in ones and zeros. So everything's got to be, so we can represent numbers, or we can use ones and zeros to represent codes, right? So what's a code? It's when we use something to represent something else, right? And that's what we get into. So we're not going to use it. Y'all can use the division method if you want to. So this is hexadecimal right here. So this gives people problems. So all of a sudden now we run out of combinations, we run out of symbols that are available to us in number system. So what did they have to, what they started doing? They started using the letters of the alphabet. So what happens now is we're going to end up with numbers that look kind of strange. Now, this is where we run into problems. If I put this guy right here, what's the problem? Well, that could be in several different numbering systems, right? So here what I'll do is make sure I subscript it with a what? 16. But we can also run into numbers like this. So if you see a B or an A or something like that, you know it can't be decimal. You know it can't be what? You know it can't be base 8. If you see an 8, you know it can't be base 8 because base 8, the highest digit you have is a 7. If you see a 2, you know it can't be binary because why? Because the biggest thing we can represent is binary. But here we can go all the way up to F. So, of course, the decimal equivalent of this would be 0. This would be 1. And we're not going to do that all the way here, but the decimal equivalent of this would be 10. This would be 11. This would be 12. This would be 13. This would be 14. And that would be 15. That's the decimal equivalent. Everybody okay? Lost anybody? So if I was counting, in decimal, I would do what? I'd go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. If I was counting in binary, I would be doing what? I'd start off with 0, then I'd go 1, then I'd go 2, then I'd go 3, then I would go what? 4, then I would go 5, then I would go 6, then I'd go 7, then I'd go 8, right? If I was counting in hex, octal, I'd go 0, 1, 2, 3, 4, 5, 6, 7. So this is decimal. This is octal. What would come next? Counting in octal. What would come next? I've run out of combinations. That's not 10, that's 1, 0. Then I go 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. I've run out of combinations, so I go 2, 0, 2, 1, 2, 2, and that's why we count in octal. Right? You understand? 0, 1, 2, 3, 4, 5, 6, 7. I've run out of combinations. Yeah, this will always equal to the base. 1, 0 always equals to the base. If I was counting in binary, I'd go 0, 1, 1, 0. That equals to the base. That equals 2. And then but here, I've only got 1 over here. Here I have 8 combinations I can put over here, right? You understand? So I'd say 1, 1, 1, 2, 1, 3. Technically, you're not supposed to call that 10, 11. You're supposed to call it 1, 0, 1, 1, 1, 2. But you'll see people in the field, they'll call it 10 and 11, 12. 14, 15, 16, 17. I've run out of combinations right here. What do it means I do? Well, I'll increase this by what? 1, and then I start at 0. So that's 16. That's a decimal 16. And I'd go 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 3, 0, right? You understand? And then I'd go all the way up till I got up to 7, 7. And then I'd add another 0 and I'd start over. Right? If I was counting in base 16, it would go what? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, I'm off whack, B, C, D, E, L. If I've run out of combinations, what do I need to do? You got 1, 0, which is equal to 16. You're exactly right. So here with 2 digits on base 16, I could go all the way up to FL. On base 10, I could only go up to 99. This, of course, would be equal to 99. That right there is equal to 255. So what's nice about hexadecimal is it's got a better resolution because we get 16 combinations per digit. Now, going from hex, so let's say I got a binary hex number. Let's see, 1065. And I wanted to go to hexadecimal. Well, the way I would have to do it, if I use the division method, is I'd start off by dividing by 16. And what does that leave me? What's that? Remainder of what? No, you can't say a remainder of 1. This is not binary. This is not going. If it's a 0.5, now what you got to understand, when I convert a number, when I convert a fraction until the whole number remainder, then we multiply it. A while ago we was multiplying by 2 because we was in base 2. So what does this thing come up and give me? 66 point what? 560. And that, y'all didn't round, right? Because if you round, you screwed up. 5 what? 5, 6, 2, 5. So what I would do is I would bring down the 66, and then I would, on my calculator, you're going to have to use a calculator. I would bring down the 66, I would come over here and multiply this by 16, and that would give me my whole number remainder. And it better come up to be less than something that's 15, right? Okay, so I'd write down a 9. Then I would come up here and I'd divide this by 16. What does that give me? Now we're not going to do it this way, but that's 4.125. I would bring down the 4, and then I'd multiply the 0.125 times 16. What does that give me? 0.125 times 16.
No.
Now, if I did this multiplication, and I came up and it came up to be 11, I wouldn't write down a 9, I'd write down a B. Y'all understand that? I'd write what it stands for. Then I'd come up here and I'd divide this by 16, which is going to give me 4, right? When I multiply the fraction. So this would be, then I would let it fall this way, and I'd say 4, 2, 9, base 16. Now that's going to be complicated because now you got to use a calculator, right? Y'all understand that? Y'all understand that? So we're not going to do that way. What I'm going to do is I'm going to come up here and I'm going to start setting up a chart of binary. So I'd go what? I'd go 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. I know it's in 2004. And then I would convert it by using what method? Subtraction method. Okay, so y'all do that for me. So now we don't have to use a calculator anymore, right? Because all this is what? Subtraction.
So you do 1065 minus 1024.
Now we're going back to what we learned first. We're taking this number and converting it into binary. So what we do is we set up a chart, then we look for the biggest thing I can subtract from the decimal number I'm trying to go to. So what's the biggest thing we can subtract from 1065? Okay, so I write down 1024, and then I'll subtract. We should be able to do that our head, right? 41. So I'm going to can't subtract the 512, can't subtract the 256, can't subtract the 128, can't subtract this. I can subtract the 32. That gives us what? 9. So I'd say 0, 1, 0, 0. So that's a lot easier. Going to binary is a lot easier than going from base 16 to hex, right? You understand that? So what I'm going to do is I'm going to come over here, and I know, by the way, what we can do in any base, we can figure out the number of numerical combinations we can represent. So, like I said, so with 3 bits of binary, we could represent 2 to the 3rd combinations. 2 to the 3rd, if you look at your chart, is what? 8. And what would they be? We got to write down the 3 patterns, and that's the way we go to octal. Well, what can we represent? Oops, what was my number? Somebody write it down. 1,000.
Oh,
And we did the binary number. What did we come up with our binary number? Wait, 1000. 100000101. Okay. See how complicated that is? Of course, if I can check it, right? 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. It's going to be 1024 plus 32 plus 9. That's it. Okay. So, how many different combinations do we have in hexadecimal? We have 16 combinations, right? And what's those combinations going to be? It's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is decimal. Now, with 4 bits of binary, that's going to be 2 to the 4th. It gives me exactly 16 combinations. So with one digit, with so with one digit, four bits of base 2, we can represent 16 combinations, right? You understand that? For each digit of base 16, we represent 16 combinations. But in base 16, I would go what? 1, 2, 3, 4, 5, 6, 7, 8, 9. What comes next? A, B, C, D, E, and F. Now, when I write down those 16, this would be one of them. This would be 1. This would be 2. This would be 3. This would be 4. This 4, Rich. This would be 5. This would be 6. This would be 7. This would be 8. This would be 9. This would be A. This would be B. This would be C. This would be D. This would be E. And this would be F. Represented in binary. Everybody follow that? But what did I use here? In octal, I used groups of 3. In hexadecimal, I used groups of 4. Everybody okay? So what I'm going to do over here on my binary number is I'm going to group this in groups of what? 4. And then I'm going to pretend there's a 0 up there. Then what I'm going to do is I'm going to write down the hex equivalent to that pattern. So what's this pattern right here? This is a 4, 2, 9. Right? This would be base 16. So let's check that out and see if it works. I don't know why I keep closing out my calculator. So I'm going to go put my thing in hex. I'm going to go 4, 2, 9. Then I'm going to convert that over to binary. Is that the same? Well, let's do binary. Let's clear this out. Where's the clear at? Right there. So I'm going to say 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1. We'll convert that to hex. 429. We can convert it to decimal, which would be 1065. Yeah, 65, right, is equal to 1, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1. And base 2, this is base 10, which is equal to 4, 2, 9, base 16. Now you can see why base 16 became a lot more popular than base 8. What would it be in base 8? Break it into 3s. Yeah, that's exactly right. So we'd take our number and we'd break it into 3s. 1, 2, 3, 1, 2, 3, 1, 2, 3. So in base 8, this would be 2, 0, 5, 1, base 8. And every one of those numbers are equal to each other. It's just that we're looking at the numbers in 4 different bases. But no matter which numbering system we're using, we've got to be able to go back eventually to base 10. Why? Because that's what we understand. I know 1065. I know what that weight is. I know this right here, right? Look at how big this number right here looks. Looks huge, don't it? Because it's binary, it's only got 2 combinations. Base 16, it looks smaller, we have 16 combinations. So base 16 has better resolution than base 10. Which means we can represent bigger numbers with the fewer characters. So I can take a base 16 number and go to, I can take a base 16 number and go to base 2. So I can come over and take a base 16 number, 3B98C, and then I'd go over and say 3B9AC, and I've converted that to binary. That fast. Now, how can I do it that fast? Because I've memorized these patterns. And what I say is, good gracious, back in elementary school, you had to learn multiplication tables. Now, y'all know what multiplication tables, that's repetitive addition, right? You understand. So 5 times 5 is actually 5 plus 5 plus 5 plus 5. But what we did, instead of doing all that math, we learned multiplication tables. We learned that 5 times 5 is 25. So I don't even have to do the 5 plus 5 plus 5 plus 5 anymore, right? I just write down 25 because I memorized multiplication tables. How did you do that? Probably with flashcards, right? Y'all use flashcards? Or you just struggle through that? So this is what's so great here, guys. On hexadecimal, on octal, all you got to do is memorize 8 patterns. On hex, all you got to do is you got to memorize 16 patterns. And instead of you even thinking about it, you just write those patterns down. So I don't, I've memorized the pattern. Right? So I know this is the pattern for what? 3. This is the pattern for what? A B. That's the pattern for a 9. That's the pattern for an A. And that's the pattern for a C. Huh?
That's hexadecimal.
That's hexadecimal binary. Normally, when we're doing this, that's what we're concerned with, right? We're concerned with, and what do we use octal and what do we use hexadecimal for in digital? To represent large binary numbers. Because I come up here and I say, okay, everybody write this down. 1 1 1 0 1 1 1 0 0 1 1 0 1 0 1 1 0 0. Nobody in this class would have wrote that down. But if I was to come up here at the same speed and say 3B9AC, how many of y'all wrote that down? Every one of you wrote that down, unless you were sleeping. So I can convey large binary numbers to you using one of these other bases. I just need to make sure that you understand I'm using octal, or if I'm using hexadecimal. By the way, the true name is hexadecimal, but just about everybody calls it hex, which is not correct, but that's just the way they call it, right? So in hexadecimal, I can convey these large binary numbers. So when my computer needs to convey a large binary number to me, it's not going to give that in binary. So in a programmable controller, if I need to enter a large binary number, a 16-bit binary number, if I start entering ones and zeros, I'm going to run into problems, right? You understand? For one reason, the box that you usually put it in is not big enough to display all of them. So you're sitting here hitting ones and zeros, and this one over here shifts out, and it don't look the same. So what I'm going to do is these guys give you the ability to enter information in several bases. So I could enter it in base 10, but when we're doing logic, decimal just don't work out. We're doing logic. We're dealing with ones and zeros. So this is what I was showing you right off the bat. All the addresses available in this computer, and it's available even on Windows 10, by the way. Windows 10, they don't put control panel in your pop-up menu. You have to type it in to get it to pop up. So down there where you usually get what Siri pop up down there on Windows 10, you just type in control panel. You pop up control panel. And then what we'll do is we'll look for Oh, this is called Device Manager. That's not what I wanted to show you, but it's still the same. This shows me everything that's available, so I can come in here and look and see. Let's see, my network adapter, and then I could come over here. This is not going to show me. This might. Resources. So this is the addresses for this device in my computer. What basis it uses. But in the computer, it's not hex, it's binary. It's just it's trying to display that to me. And if I was trying to display that 16-bit number, which would have been what? 6 would be 11000001011000 through, and then I would go through that. It would be very confusing, right? Even though I do understand binary, just me transposing that. But 60B0 through 60B7, that's the range of that. And look at the memory. Good gracious. Each one of these represents 4 bits. So that's 1, 2, 3, 4, 5, 6, 7, 8. That's a 32-bit number.
Why do they have all those zeros from those?
Because they always display it with the same number. Sometimes they'll display it, they'll put an X out there indicating this X is replacing a bunch of digits.
Okay.
Yeah, we're into these processors here have a ton. So we have 2 addressing ranges. We have the addressing range for the device itself, and then we have an address range for the memory that device uses. So every physical device in the computer has an address. So if I want to send something to this display has an address. And this might not show up here because it says monitor. Oh, here's display adapters. So here's the display adapter. That's the driver. Oh, here we go. And here's the resources that thing uses. So the display adapter itself is at this address. That's the I/O, and this is the amount of memory that display uses. So we have 2 different addressing ranges. We have for the device itself, and then for the memory that device uses. So everything on this computer, this keyboard's got an address. Y'all see, there's keyboard right there. I hope no, it don't show it. The other place, that's the other place you would go to actually see the entire map. You go to accessories, and then system tools, and then system information. So this shows you everything. So this would be I/O. And then the display should be in there somewhere. But instead of it displaying, so your these computers use 16 bits for I/O address. So they have 65,536 different devices. And then it uses a ton for memory. So see the X right there, that's replacing all those bits. So that's a 1, 2, 3, 4, 5, 6, 7, 8. So that's a 32-bit number, which would give us 131 billion, right? That's 2 to the 32nd. I'm sorry, 2 billion.
36 or 4 billion?
Yeah, 4 billion. So that's the numbering system, guys. So anything we need to go back through. So what we're going to look at next class, and then we'll get into actually digital, is codes. You know, what do we use a code for? We're we're just gonna get a little introduction to this.
So when you come to Charlotte,
Oh, by the way, this is what I wanted to show you. This is the shuttle. And the shuttle, basically, they make everything easy for us, but you gotta understand, this computer only processes binary information. So instead of having a big old keyboard like this when they program that computer, can y'all see the keyboards on the shuttle?
Homie,
0, right? Look at that. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So when they had to do reprogramming of the computer up there on the shuttle, they did it in what? Hex. Hex. Did y'all see the movie Martian? So he wanted to send text information back to NASA. So what did he use? He used a code. So the first code we're going to look at is going to be called the American Standard Code for Information Interchange. This was the code that the guy, who started in Martian? That's a good movie.
I need to watch it.
It's a good movie.
I've seen it, but it's been a long time since I've seen it.
Wahlberg,
Mm-hmm.
yeah. McDane, yeah. The guy, same one that does Bourne, Justin Bourne. He gets stuck up on Mars by himself, and he's trying to communicate with Earth, but everything's gone. So what he does is he finds one of the I think it's one of the little rovers that comes around. It's got a camera on it, and he uses ASCII code to send them letters. And then they showed him how to reprogram that thing. But ASCII code is a code that we can use to send characters. And ASCII code's been around for years. You'll see it pop in science fiction movies every once in a while. So this is the code. And of course, this is a chart we'll look at right here and learn how to interpret this. Now, Matt didn't use binary. Matt used hexadecimal. So it's a binary code of ones and zeros. But now we know we can take a binary code and convert it into another numbering system. So this guy here gives me 256 combinations, all the way from 0, 0, 0, 0, 0, 0, all the way up to 1, 1, 1, 1, 1, 1, 1. But I can represent that with 2 digits of hex, which only gives me 16 combinations now, right? You understand? So that's what Matt used. I'll try to cut that video out and show y'all what he did. He looked it up in a chart. So the codes we'll be talking about ASCII code. Now the problem with ASCII, we only get 256 combinations, right? It's a 7-bit code. 2 to the 7th gives us 2. So that's the way we can find the number of combinations. We take the base and then we raise it to the number of digits or bits. So it's a 7-bit code that gives me 207 255 combinations, 2 to the 7th. Right, 256 combinations.
Playing with numbers today.
No, we're just
running together.
this is the same chart in hex, and then of course the other code we're going to look at is a code we use now called Unicode, and you've probably seen that before. When I come over here and tell it to insert a symbol, see right down here, can y'all see this code it's using? It's using Unicode, a code called, it's using the hexadecimal number system, but this is a code called Unicode. This is what we use on the internet now. The internet uses Unicode. So we'll look at that. Unicode is rough, but you'll get an understanding of Unicode. So these are the codes we'll look at next class. Okay, guys, here's the worksheets. Y'all don't need to do the BCD yet. So BCD is a code too. So I forgot about that. We'll look at ASCII. We'll look at binary coded decimal, and we'll let y'all look at a little bit on Unicode. So y'all see how this works? So just ignore the BCD part. We'll come back and figure that later on. Everybody okay? Y'all see how this works? I give you a number in one base and then you have to fill in the other square. Everybody okay? When's this due?
Yeah.
Wednesday. Okay? Everybody got one? Y'all got any questions on it? Everybody okay?
It to be a case.
Y'all Wednesday.